It's like 100 degrees in the valley today, so I feared like 5,000 feet would be the coolest place to record lectures. So enjoy!
Hey everybody, welcome back to our series on Vertex Operator Algebras. Today we are talking again about affine algebras, but this time with a twist. First, a quick untwisted review. Remember that we can build an affine Lie algebra from a Lie algebra G using the Laurent polynomials and a central extension, which affords a slightly complicated bracket structure. To learn how to twist this construction, we first need to discuss isometries of the inner products of Lie algebras. An automorphism of some Lie algebra G is called an isometry if the inner product is invariant under it. If it helps, you can think of this as some kind of coordinate frame transformation, like a rotation. An interesting class of isometries are the involutions, which are those that square to unity. Involutions are crucial to the study of finite simple groups, and will give rise to a Z2 grading on G. Define the subspaces G sub I by the eigenvalues of the involution. These are often known by the more familiar monikers even and odd. As a quick exercise, you can verify that G0 and G1 are orthogonal with respect to the inner product. Also, the commutator of two even elements is even. One even and one odd element is odd, and two odd elements is even. Let's now talk about involutions on Laurent polynomials. To better illustrate an involutive action, let's consider the Laurent polynomials in the formal variable t to the 1/2. We then consider an operator nu that takes t to the 1/2 to minus t to the 1/2. This way, the algebra of polynomials in t to the 1/2 breaks naturally into even and odd subspaces, those of integral and half-integral powers of t, respectively. Now let's combine these ideas to form an involution, theta, on the affine Lie algebra G hat. Here, the action of theta on C is trivial, but the action of theta on terms like x times f is theta sub g x times nu f, where theta sub g and nu are the involutions we discussed earlier. As FLM points out, the application of only nu on G hat is a totally valid involution on G hat, but it's a different one from what we're considering. We are interested in the case that twists G together with the polynomials in T. The affine algebra G hat twisted by theta is defined to be the space of all elements in the half-integral graded affine Lie algebra that are together invariant under theta. Notice how this twisted affine algebra decomposes into three subspaces: even, odd, and central. As with the untwisted case, we can append the derivation to G hat of theta to form the extended, twisted Lie algebra, twisted by theta, virgulia G of theta. As with the untwisted case, eigenvalues of the add D operator give a natural half-integral grading to the extended twisted algebra, which is inherited by the twisted algebra. Of course, if the involution theta is trivial, then these twisted algebras reduce to their untwisted counterparts discussed yesterday. FLM reminds us that this kind of construction can be done with any automorphic isometry that is of finite order. So it needn't be square to 1, it could triple to 1, or quad to 1. We just study the involutive case because it happens to be relevant for finite simple groups, particularly, of course, the monster. And that's all for today. We'll put this technology to use soon when we study representations of the Heisenberg algebra. The Heisenberg algebra is our topic for the next lecture. See you tomorrow.